This is the short summary for addenda to chapter 3. The addenda were motivated by the feeling that I did not explain the Curry-Howard correspondence very well. And also I was working on a Curry-Howard library and I wanted to present that library. I recapitulated some of the main ideas of the Curry-Howard correspondence, and I showed that if you take a function whose arguments have fully parametric types, then in some cases you can completely determine its code from the type. In some cases you can decide that the code is impossible, and in other cases you can have several implementations, but only one of them is really useful. Others always return empty results, and so they're not useful. I present my Curry-Howard library, which consists of this call to implement a function that is given by its type. So you don't write code yourself, you just say this is the type of the function in the Scala syntax, and you just say equals implement, and that's sufficient. And another way of using the Curry-Howard library is to say of type, and then you say of which type you want to get a result, and then from what parts to build that result, and it will try to automatically find code for that. So I explain how that works with some examples, and I can implement some non-trivial code for some functions like that. And I also can show that there is no implementation. If there is no implementation, it's a compile time error to use implement. Then I explain how that library works. It works by an algorithm that finds a proof for a logical formula, if possible. I show what it means to find proofs. I explain how logic finds proofs using the so-called sequence and rules of derivation. Each rule of derivation transforms one sequence into one or more others that needs to be proved. Now, each sequence is a proof task, and the rules of derivation say that to prove one, you need to prove several others, perhaps. And some of the rules are axioms that tell you what can be proved already with no further work. And so I show on an example how these rules can be used to find the proof for this formula, which is a theorem in logic. So I find the proof. Also, I show how the code is generated from the proof using the so-called proof transformers. And step by step, I trace the proof back from the final sequence to the initial and show how the expression is built up by parts. And this is the code that represents this type. So in this way, the Curry-Howard library can deduce code from type signatures. I show the so-called calculus LJT, which is the set of rules actually used by the Curry-Howard library. And I show how that calculus is related to the previous one, and comment on when we can use this and when we cannot use it. And after this, I decided that actually my Curry-Howard explanation was too short. The Curry-Howard correspondence is a more difficult topic, and many people want to learn about it, but there isn't a good tutorial on the internet anywhere. So I decided to make a very clear and detailed tutorial, and this is it, the second addendum to chapter 3. I explain in detail what are the type constructions that we have in the functional languages, such as tuple, function, disjunction, unit type, and a type parameter. I show examples in the Scala syntax how all of these types are created and used in the code. And also I show for comparison the same exact constructions in the OCaml programming language and in the Haskell programming language. I show how similar they are. The syntax is different, but it's extremely similar. The way that you have these constructions created and used. I again reiterate how types are related to propositions and what it means to have the proposition that code has a value of type t. And I use a short notation where I contrast the notation used in logic and in the types that I use. And I advocate that this notation is to be used when talking about types in a programming language, and this notation is to be used only when talking about formal logic. I explain in detail what a sequent is, what its premises and goal, and how formal logic uses axioms and derivation rules to build proofs. And I also give an example of how sequence corresponds to expressions in code, in Scala, for instance. This is an important correspondence because actually it's a sequence that we're going to be proving, and the proof of a sequence corresponds to code. That's how we want to derive code from logical proofs. In order to make proofs, we need derivation rules. So I list the derivation rules that follow from the constructions of language that we just iterated before. And I explain why the notation is useful like that. It's the standard conventions of algebra and a standard convention of functional programming for this notation. I explain also about the quantifiers, how we use quantifiers in this situation. It's important that actually in this consideration all type variables must be universally quantified. We will not write this explicitly, but on the outside of each formula there are universally quantified variables that are inside. So always outside of each formula there are universal quantifiers. I give an example of theorems and how a derivation of a theorem actually creates code. So in this way, the Curry-Howard correspondence is a direct correspondence between logical derivations and actual code that you can write. And this is one side of the Curry-Howard correspondence that is directly useful for deriving code from types. So I show that logical statements, which are always going to be of this sort with universal quantifiers outside, logical statements that can be proved correspond to code that can be written, and non-theorems cannot be implemented, do not correspond to any code. I also show that the logic that we need to use, in other words, the logic based on these rules, is not classical logic. It is not the same as Boolean logic. I give a specific example, which is maybe slightly counterintuitive, but I talk about this in detail. Implication works differently and disjunction works differently. Now, I discuss this logic in some more detail and show that there are different libraries that implement the proof search for this logic. I give the rules. These rules follow directly from our language constructions Here they're just written in the notation that logicians prefer. But these rules do not help to obtain an algorithm, a search tree for the proof. So mathematicians have found different sets of rules that are equivalent, but much more directly translated into a proof search. And I again give the example that I gave before with this proof, how the search directly gives you a proof for some proposition. I show that this calculus, which is the LJT, is better because it does not have a loop. There's a loop here in this proof, as I show, but here there is no such loop. And there's a proof in this paper that there's no loops. So I comment on this theorem that mathematicians call trivial. I explain that this is just a figure of speech. It's not at all trivial. Now, if you want to translate proofs into code, you have to transform each step in the proof into some code. And that is what proof transformers do. They assemble code little by little, piece by piece. And I show explicitly how that works in two examples of proof transformers. So they give you little chunks of code like this that you assemble then as you go from the proof into code. So this is how it works for the proof shown before, and after simplifying the code we get the expression, and that's how the Curry-Howard library works. Now I explain in more detail how the type isomorphism works. These are the logical identities, but they do not necessarily express isomorphisms, and I go in detail about showing when they do and when they don't on various examples, and I explain why in some more detail than I did in part 3 of the main lecture. So this reiterates the conclusions about what we can do. We can automatically generate code, and however, we cannot generate code when there are some additional properties, so I explain what the limitations are of the Curry-Howard library. And here are some notes that didn't come into the lecture. And I conclude again with my picture of how programming language design can be informed by the correspondence with formal logic.